All right, excellent. Good. Okay, so I'm going to welcome everybody. I'm going to talk about approaches for planning, managing under these conditions of deep uncertainty, so which we've touched on a lot, and you'll see this is really building and fleshing out a lot of the topics that Joel just discussed. Okay, so let's next slide, please. Great. So you've received a lot of advice so far. Past climate, the way we've usually in the past is that we've assumed that future climate could be well represented by past climate. It's pretty clear that that is no longer a viable assumption. Even for current climate is not the same as past climate. Climate models are helpful when used appropriately, but far from perfect, though it's always worth noting that they're probably actually a lot better than many of the economic models we use to forecast the future of our regions. We really can't wait for the uncertainties to be resolved. Reducing uncertainty is an important part of the portfolio of things to do, but we can't wait around for that to happen, because they'll never be resolved completely. So we need to act in the face of uncertainty. We need to consider multiple objectives: reliability, cost effectiveness. We discussed earlier as part of the game, balancing between the physical safety and advancing development and well-being. So we need to consider these multiple objectives, not any single one. And what we're really looking for are decisions that are going to prove effective or provide benefits under many possible future conditions. Joel touched on this. And as the final piece, give a click. Yeah, great. And we should not mistake well-characterized risk, which is where we started out in the game with the die, for another click. Yeah, for deep uncertainty, which the cone we left with at the end is sort of a physical manifestation, a nice attribute of deep uncertainty. Okay, so next slide, please. Okay, so DMDU methods, decision-making under deep uncertainty, methods and tools provide the means to take this advice. And so there's 4 basic principles, and then I'm going to take you through an example that fleshes these out. But consider multiple futures, not a single one, in your planning, and choose these futures to stress test your plans, to understand where the conditions where they're strong, where they meet goals, and conditions where they may fail to. We're looking for robust plans, ones that perform well over many futures, and not ones that are optimal for any particular best estimate future, because those can often be brittle. One way to achieve these robust plans is to make them flexible and adaptive, so that they're designed to adjust over time, and the actions we take in the near term make that easier and possible. And finally, use your analytics to explore futures and options, not to tell you what to do. So really, the data and tools are to help you understand trade-offs, the key drivers, things which are most important, which are less important. They're really not going to make decisions for you. And so water managers already conduct risk management. DMDU is really sort of another layer on your risk management that helps you deal with these more poorly characterized uncertainties that characterize the world that we now live in and will for the foreseeable future. Next slide. Next slide. Okay, great. So just to put in perspective what we're trying to do here. So traditional risk management is designed to work well when the uncertainty is limited. So there's a whole set of fabulous methods and tools that fall in this general category. But the basic idea is that we first come to a common understanding of what future conditions will be. And sometimes this is a forecast, a single forecast. more properly, it's a joint probability distribution over multiple states of the world. And once we have our understanding of future conditions, then we can rank different decisions about how well they're going to do given that those future conditions. Again, the most formal methods, we have a utility function, and we calculate expected utility. That gives us a best strategy. And then we may do some sensitivity analysis to see how sensitive our decision is to these to various assumptions. So the label that we stick on this is predict then act, because, or sometimes called, Joel, I think, mentioned optimization method. Predict then act because these understanding of the future conditions, this prediction is the input to our actions. Now, there are many situations where that predict and act works fabulously. I always say you'd never get on an airplane where the people who built it and flew it didn't work really well in these situations. But next slide. One of the things that the people who build and fly airplanes have the luxury that if they're worried about not being in conditions that they don't understand, they can just not fly, which has happened to all of us. It's annoying, but it's a good thing. But for those of us, for those who run water agencies or deal with problems like climate change, you don't have the luxury of just not doing anything, or just saying, well, we'll wait till the uncertainties are resolved to figure out what to do. You got to keep sailing through them. And when uncertainties get deep, predict then act and break down. Next, click. Yeah, so under conditions of this deep uncertainty, there is often a lot of pressure to underestimate uncertainties, because if you really open up the aperture and admit how big they are, then you can't do the planning. Competing analyses contribute to gridlock, so that a proposal is predicated on a prediction. People who don't like the proposal, for whatever set of reasons, often find it best to attack the prediction as opposed to the plan itself, because the prediction, the plan may have virtues, but the prediction is likely to be wrong. So it's an easy target. And then this idea that we know a lot about a problem that can help us help us find good solutions, but which may not be very predictive information. So essentially, the search for predictions can cause us to spend a lot of effort trying to figure out what the future is going to be, rather than figuring out the best thing to do given our understanding of the future. Okay, next slide. So what do you do? Well, these DMDU approaches, in some sense, run the analysis backwards. So instead of starting with these future predictions, we start with our goals and our plans to get there. And then we use our analytics to stress test what we're planning to do and ask questions like, under what conditions does this plan meet its goals, and under what conditions may it fail? So this in many ways allows us to use our analytics to give us much higher confidence answers, even in a world of deep uncertainty, than we get through a predict and act way. So for instance, we can understand if we're worried about floodwaters, we can calculate how big a flood would cause a problem for a particular neighborhood or a particular facility, even if we don't know then the likelihood of that flood. But we can say, well, if the floodwaters got this high, we would have a significant problem. Once we've done these stress tests, then we can use that information to identify new or revised strategies that are more robust, that is, work well over a wider range of futures. And then we can iterate once we've got a candidate more robust plan, we can stress test it again and iteratively move to more robust strategies. Okay, next slide. And so again, I mean, DMDU is designed to help people make better decisions, not better predictions. Here are our principles. Next click. And so instead of this, click again. We're trying to plan over multiple futures. One more click. And here is a formal definition of deep uncertainty, which relates it back to the risk management literature. Deep uncertainty occurs when the parties to a decision do not know or do not agree on the likelihood of alternative futures or how actions are related to consequences. So basically uncertainty or imprecision or just lack of knowledge about the probabilities or an imperfect understanding of the model of if we do this, we get that. So the game was clearly designed to move from a condition of well-characterized uncertainty when we had the dice rolls to a condition of deep uncertainty when we had the cone, and even before that, when you were started to be unsure about what die you were actually going to have. Okay, next slide. Let me take you through an example now to show you how this works in practice. Okay, next slide. Okay, so I'm going to talk about one particular form of decision-making under deep uncertainty called robust decision-making. This is the approach that's used at RAND often, and then various other places. And at the end, I'll expand the aperture a little bit and talk about some of the other approaches to deep uncertainty, where you're going to see some examples from other agencies later on today. So this is a study we did a couple of years ago with the city of Los Angeles, and looking at the city's ability to meet water quality goals in the face of climate change. And I choose this example because it's relatively straightforward, and it has a focus on extreme events, which I think is an interest in this session. Okay, so next slide, please. So the city had gone, oh no, back again. Yeah. No, back please. Yeah, great. Yeah, great. Okay. So the city had come up with a plan to meet federal water quality standards by 2035. They had a series of, they were doing a standard predict and act analysis. They had a set of optimization models. They ran them and came up with this percentage of distribution of best management practices based on their best guess predictions. And so regional projects, big spreading basins, that sort of thing, capture about 45% of the runoff. Green streets, which are more permeable pavement, capture about 22%, and low impact development, which is capturing water on private property, captures about 33%. So that was the best plan. But it was made under the assumption that we know future climate. So we helped them ask the question, is this plan going to work in the face of climate change? Next slide. So we went through these steps, which are essentially the checklist of steps in the RDM process. Step one is frame the decision challenge. What are we trying to achieve? What actions might we take to achieve our goals? What uncertainties affect our ability to meet to achieve those goals? Then once we've done that, we can take our models and data to stress test proposed strategies over a wide range of futures, identifying the most important factors affecting whether we meet or miss our goals. And then we can use that information to devise new or revised strategies that work better in the face of uncertainty. So next slide. And just to note that this checklist should look familiar because it's just the steps I showed you on the DMDU backwards analysis. Next slide. Okay, so let's start with decision framing. Next slide. Okay, so we start out with a question, a policy question, which in this case is, will our expensive new water quality investments still meet their goals in a changing climate? And if not, what can we do about it? So we work with the decision makers, we talk about the problem, and then it becomes useful to divide the factors we're discussing into these 4 quadrants, which we call XLRM. Click. So the performance metrics, the M's, are what are we trying to achieve and how do we quantify those? Click. And the L's, the policy levers, are what are the actions that we might take in combination to achieve those goals? Click. The uncertain factors are what things outside our control, like the climate, affect our ability to pursue these goals, and click. And the relationships are then the models and data that we use to connect the levers and uncertainties. So we're going to do this, we get this world, and to the outcomes. What outcomes does that have? So in this particular case, click, it looked like this. The goals were meeting water quality standards and being cost effective. The policy levers, we started with the proposed plan, and then I'll show you, we looked at some ways to turn into an adaptive plan. The key uncertainties we're looking at is climate change and the future of land use in the city. And in this example, we use the hydrology and optimization models for the best management practices that the city was already using in the regulatory approval analysis. So this is not any new models. This is just using the models they were currently using, but in a slightly different way. Okay, click. Yeah, and the most effort in the analysis went into the R's and the X's. Okay, next slide. Okay, so now we're going to do this stress test. And let me show you how this works. Next slide. Okay, so we have the plan and we have uncertainties in land use and climate change. Click. And so we take our models and we run the plan over a wide range of assumptions about future climate and about future land use. So we get a whole bunch of cases. So we got a cloud of points. The blue dot means that the plan meets the goals. So we do a run with assumption about the future, the plan, and then we see whether we meet or miss the water quality goals in that case. And so if we meet, we get a blue dot. If we miss, we get a red dot. Okay, so a lot of different outcomes. What do we do with that? So click. So we run some statistical packages against this database, classification algorithms, and we ask the question, of all the uncertainties, what two uncertainties should I put on my axes? And then where do I draw a line in that coordinate space that does the best job of getting the red dots on one side and the blue dots on the other? And this turns out to be the answer. And what you see is that the two most important things are the change in 24-hour rainfall intensity. So this is essentially the incident of extreme events, and the impervious area of the city. And so a 1 on the horizontal axis means that the intensity of the 24-hour rainfall event doesn't change. A 1.2 means that it's 20% bigger and then 40% bigger. And then the impervious area is the area of the city that does not absorb water. So going down means you're absorbing more. So the horizontal lines are each a different assumption about city land use, and then the dots along there are the results of different climate models. The X is the planning case that the city used, and not surprisingly, that's well in this region on the left, where you have mostly blue dots and the plan meets goals. But you see it's pretty close to the red area, where you have all the red dots and the plan misses goals. So the current plan may not be particularly robust or resilient in the face of climate change. In fact, if the intensity of the 24-hour rainfall, 95 percentile 24-hour rainfall event increases by just a little bit, then the plan begins to fail. However, if they have much, if the land use planning in the city manages to significantly make the surface of the city more absorbing, in particular, they reach the goal labeled newly mandated land use, they buy out a lot of climate uncertainty. Okay, next slide.
You've got about 3 or 4 minutes left, Rob.
Oh my God. Okay. All right. I will. I'll finish up quickly. Okay. Great. So, should we worry about that? Click. Yeah. So well, first off, how might we respond to this? Well, let's do an adaptive plan where we're going to start with the plan, monitor signposts, and then do contingent actions if signposts are reserved. So we can use the stress test results to map that out. Click, please. Okay, so we could begin with the current plan and take it out to 2035. Okay, click. And we could watch how we're doing with land use and what the climate scientists are saying about these extreme events. And if the city is failing to get the new land use plan, or science cannot guarantee the storms stay small, we might do an augmented plan. Click. Which would be designed to work in the red area. So we can calculate what that would be more regional projects, etc. Click, please. Or if we don't see those, we can continue with the current plan. So this is an adaptive plan that begins with the current plan and then monitors to see whether it should augment. Okay, click. And is this something we should worry about? Well, yes, it is, because I won't go into it right now, but we did a couple of bounding cases on the range of scientific opinion, and it basically covers all suggests, no matter which way you look at it, it suggests that the current plan is vulnerable to climate change unless you can get these land use changes. Okay, click. Okay, so we can do a little bit of multi-objective trade-off here. We have 2 objectives, water quality and cost, and we've got a couple of different options. We can stick with the current plan. We could do the current plan, prepare to adjust, or we could begin with the augmented plan and begin to adjust. We've got 2 scenarios. The one on the left is the current plan meets goals. The one on the right is the current plan doesn't meet goals. And what you see is that in the plan meets goals scenario, the current plan does best on water quality and cost. This begin with current plan, prepare to adjust, does well on water quality, is slightly higher cost, and the augmented plan is higher cost still. But in the other scenario, the current plan fails on both attributes. The begin with current plan, prepare to adjust meets water quality goals, is slightly higher cost, and the augmented plan is best. So this middle one, looking across the scenarios, click, is our low regret strategy, because it does okay, not the best, but does okay pretty well in both strategies. Okay, when you click, I'm going to click again. I'm going to skip the next slide. Okay, this has to do with surprise. We talk about that later if you like. Click. Yeah, so just key attributes of what we saw. We did multi-scenarios, so we had lots of scenarios. We had several objectives. It builds on the agency's single scenario analysis. We did lots of model runs, clustered them into 2 policy relevant scenarios. There was a focus on extreme precipitation events and land use changes as the drivers of vulnerability for the current plan. We used the probability ranges to interpret the implications of the scenarios, not as inputs in the analysis. And we found that an adaptive strategy was robust. Okay, next slide. Yeah, and just to say that there's increasingly data to support such analyses, and the Mid-Atlantic MARISA, of which RAND is one of the members, has been producing IDF curves for the Chesapeake Bay region, which have this character of showing a wide range of scenarios, and they're really designed to help inform the results of the stress tests, like I just showed you, where you can do the stress tests and then lay them against these range of values in the IDF curves to see whether a particular plan is robust across the range of uncertainty or might need to be adjusted. Okay, next slide. And just have one or two more slides to finish up. So there's a variety of different DMDU approaches. I showed you this robust decision-making. You're going to hear about scenario planning and adaptive pathways in the following talks. Then there's another approach called decision scaling, which is used a lot in California, which is essentially a version of robust decision-making. Clicks, please. And here's essentially how they work. So scenario planning develops robust strategies from scenarios that people create. Adaptive pathways provides a framework for developing strategies that adjust over time. RDM does roughly the same thing, but is designed for places where the vulnerabilities are more complicated and multidimensional, and decision scaling focuses on the vulnerability analysis part of it. So one more slide. I should say that all of these, they're different flavors of essentially the same thing. So these tools can be a very useful way to both think about the challenge of climate adaptation and a changing climate, and give you some concrete steps and tools for doing your analyses. The current and future climate is not the same in the past. Click. To deal with that, consider multiple futures, choose the futures to stress test plans, seek robust plans, not optimal ones. Plans should be flexible, adaptive, and use your analytics to explore many futures and options. And one more click. And I think that's supposed to spin around, but it's not going. Yeah, there we go. Okay. Yes. All right. Thank you.